Hey, thanks, John, for this very nice introduction. I'm going to see if I can share my screen with you guys. Okay, so you should be able to see my notebook now.
Yes.
Good. Okay. Yeah, let's get started. So my part will be about a subspace constraint reconstruction of frequency modulated SSFP data. And I will explain, first of all, how to use BART to do this kind of reconstruction, but also how this fits into the general concept that that John was introducing, basically. So yeah, if you want to read the paper, our paper is here. This is frequency modulated SFP data I gave the DOI, and also the raw data that I used for the reconstruction can be found on GitHub. Okay, so you need some prerequisites. You have to make sure that the toolbox path is set correctly. So we can do that by basically checking our BART version, and we recommend that you use the most updated version. So the freshly released 0.7 version should be best for this. Okay, we also need a few helper functions. So basically two to look at what we generated. So this uses the special tool that comes with the viewer tool that is also available, kind of comprehensive to BART, so that we can look at magnitude and phase, which is kind of interesting in this particular subspace-based reconstruction. And then also show time steps. It's just a helper function that let me show different images within a time series. Okay, so just like a brief background, so not everybody might be familiar with frequency modulated SSFP, but I guess you are familiar with balanced SSFP. So balanced steady state free precession is a sequence that produces a very high SNR. It's actually the highest SNR of all steady state sequences. However, it suffers from banding artifacts or signal voids, depending on off resonance, so depending on the shim, basically. If you want to get rid of these banding artifacts, one option is that you do phase cycle balanced SSFP. That means you acquire multiple images with different transmitter and receiver phase increments, and then you can combine these images to form a banding-free image. However, you have to establish different steady states. So you have some kind of transient phases or compromises how to get into these steady states. And then last but not least, frequency modulated SSFP. This is a technique that was proposed by Foxall et al. In 2002. And they demonstrated that balanced SSFP sequences are actually tolerant to small but continuous changes in the phase increment. And if you do that, if you change the phase increment continuously, then you basically sweep through the entire frequency response spectrum. And this is time efficient because you don't have to establish individual steady states. You kind of stay in this dynamic steady state and sweep through your entire spectrum. Okay, so here's a plot what this looks like. So this is a typical frequency modulated SSFP signal that I simulated with extended phase graphs. So on the left, you see the rise of the signal, then this sharp drop, this kind of banding that you transform into the time domain now, and then it is almost symmetric and then comes out of this dip again. And if you look at the Fourier transform of that signal, then we see a very sharp drop off around the innermost Fourier modes. So that basically tells us our signal is very, very smooth. And so that might already hint that the low frequency Fourier domain is a very good subspace indeed. Also, if we shift the signal, which could easily happen by some off resonances, then of course that won't show up in the magnitude of the Fourier domain, since this is just a phase shift, which is also a nice property. So it would be invariant to shifts. Okay, of course, this is only one parameter combination that I picked here. So we have to confirm that indeed the low frequency space is a good subspace for all combinations of parameters. But we can easily do that by just looking at different combinations of parameters. So here I varied from left to right T1, T2, and also the flip angle. And you can see that the amount of energy that I explain of the signal is pretty high if I constrain myself to a subspace size of, say, around 8 subspace coefficients. Then I explain in all cases more than 80% of the signal, but in most like realistic parameter combinations, even 90% or more. So that means we can use the low frequency Fourier domain as a subspace. Okay, so we have to load the raw data. So the raw data I provided here, this is actually originally from a 3D stack of stars encoded data set. But here, for demonstration purposes, I just consider one single slice. So I obtained that after doing the inverse Fourier transform along partition direction. And if you look at the dimensions, we can see it has 384 readout points, 404 spokes, and 58 channels. So this was a head coil I did this a brain experiment with. So this volunteer experiment. Okay, so let's look at the raw data. I can also run this again. Oops, oh, I can't. I didn't run my helper functions. So let's quickly do that. Okay, and now let's look at the raw data. Okay, so we should be able to see, right? So in the magnitude representation, we can see that there's this periodicity, which comes from the golden angle sampling that I employed here. And if you look at the corresponding phase, depends a little bit on the position of the actual coil, but we can also see this nice sweep through the entire spectrum. So the phase changes continuously with time. Okay, so for the actual reconstruction, we have to pre-compute a few things. So first of all, the Fourier basis. So in that case, it's quite easy. We don't have to do any SVD or signal simulation. We just create the discrete Fourier transform matrix basically and crop it to the innermost columns. So here I picked a subspace size of 8, and then we can use the BART delta command, which does the Kronecker delta basically, and we can create a P by P unity matrix. I just zero pad to match the time dimensions for the number of spokes that I acquired. Then I do the FFT, and this is my basis already. And if we look at the dimensions, we see, okay, we have 404 time points, which is in the echo dimension here, in BART's echo dimension. And then we have 8 coefficients in the coefficient dimension. Okay, then for the actual reconstruction, we also have to create the trajectory or build a trajectory that matches the one that I used for scanning. So in that case, was a golden angle trajectory. And I can create this with this trajectory tool of BART, telling it I want a radial trajectory that also contains the center of k-space for each spoke. So it's kind of asymmetric. Dash capital G is for golden angle, a certain number of spokes and readout points. And then I reshape it. However, I also want to compensate for possible gradient delays. So what I do here is I crop out the first 5 spokes into a subset, and then I use the BART S delay method, which is the ring method that a coworker of us came up, Rosenzweig, in 2018. And it performs this gradient delay estimation on these 5 spokes. We can also run this. And then I can't go into details, but this basically tells you how much delay there is in the logical coordinate system. And then, of course, we want to use these determined delays now to create a trajectory that is corrected for these estimated delays. So that is the actual trajectory and not just the nominal trajectory. And this goes into this stretch_1. Okay, for the sake of time, I'm not going to explain this shell completely, but what it does, and I try to leave some comments that might help you guys if you want to figure this out. It does just channel compression, it compresses down to 10 channels, does the inverse NUFFT to get calibration data for E-spirit. What we can do is we can look at the actual coil sensitivity profiles after channel compression. And we can see that this is definitely channel compressed. This is no longer physical coils. These are now virtual coils with this corresponding, fascinating phase profiles also. Okay, then we have everything together. We can use the basis now and also the sensitivities that we just determined for the actual subspace constrained reconstructions. Okay, so we can also run this. As usual, we have to specify a few parameters. So the first one would be the regularization strength, kind of manually determined here. The block size for the local low rank regularizer that I'm going to use, and how many Pfister iterations I want to do, 100 in that case. Okay, we have to transform the data to match the required dimensions. Here, this is meant to be a toggle, right? So if you're on Binder, you can just set this to true, and it would just copy the pre-computed result that I did on my local machine. If you were on a local machine, you can just run this command. It should be relatively fast. So I think it takes around maybe 2 minutes or so. So we should see the iterations coming up soon, actually. Okay, so when you run this command, as John was mentioning, the most important difference to the previous pix command is this dash capital P. So now we just provided the basis with the corresponding correct dimensions, time, so echo time and coefficient dimensions. Then of course the measured raw data, the sensitivities, and then the reconstruction result would be written into out. I also have a few flags here that I want to briefly explain. Dash E scales the step size based on the maximal eigenvalue of the normal operator. So this is a quite helpful flag. Dash D5 in that case is a debug level. So this is where we see all this nice stuff coming out. And then finally, dash R allows me to specify what kind of regularization I want to use. In that case, locally your rank regularizer with spatial decimation as well. So this is this 3-3 would be 7-7 if I did a 3D reconstruction. But this is just a single slice, as I was mentioning. Right. So what can we see here? I don't want to go into details. Worth mentioning is definitely that when BART builds these operators and strings them together, you can see that it builds this NUFFT point spread function. And if you look at the dimensions, you see, okay, it has spatial dimensions now and this coefficient dimensions, but it doesn't have any time dimension anymore. So that means the actual reconstruction is solved in subspace, which is nice, both in terms of computational demand, but also in terms of memory. You don't have to store all individual time points. Okay, so then let's see if it's already done. Almost. Okay, so you can see the residue reducing. Oh, not always actually. Okay, so just give it 10 more iterations, and then we should see the final results. Okay, good. So here I just crop and transpose the reconstruction result to the correct FOV and to get the anatomically correct orientation. So nothing magic happening. I also flip to get a consistent order of the coefficients so that it matches with the graphics that I was showing above. And if you reshape and look at the data, then it looks like this. And we can compare this with the sketch I was showing above. So now we have 8 subspace coefficients. We can nicely see this drop off. So the signal is really concentrated around the 4 innermost coefficients, and it drops off to the center. And also the phase has this interesting structure where with respect to higher coefficient orders, this this imperfect shim that I used here is kind of amplified, and you get this nice stripe pattern. Okay, so that matches with this Fourier domain plot here. Of course, we can also do what John suggested. You can always just back project and go to time domain again. So let's do that. We use the fmec command for that and use our bases, and our coefficients are already here. So that's straightforward. We get a time series, and then we just look at very few time points in this time series. So that would basically be synthesized phase cycle and balance of P-like images. So in the time domain representations, this is what that looks like. So you can see we get these nice banding artifacts here, depending on where we are in this time series. So if you would play this in a movie, you could see them like shifting through your FOE. And also this particular well-known alternating phase pattern from balanced SSFP. Right, but of course, well, now you can tell, okay, I did my best to create a very linear shim gradient here in that case, a linear phase gradient. Okay, but of course, if you want to have banding free images, then you would try to combine them in a different way. You could, for instance, do root sum of squares combination. So just taking the subspace reconstruction, the result, the subspaces, and sum them up in that way, and then you get one banding free image that is very close to a balanced SSFP like contrast. And of course, it doesn't have any phase anymore. Right, so that is from my side. I'm not sure if we have time, but if there is, then don't hesitate to ask questions.
Thanks, I think we do have some time. I know that some people were setting up at the start. But any general questions about that? So yeah, Volker, I really enjoyed it. I had just a quick comment I wanted to make. If you could just scroll up a little bit to even hear that previous cell where you were. Yeah, right here. I just wanted to make a comment that if you're looking at this and you're fairly new to BART and you see these commands that are being used and you're not sure exactly what they're doing, then you can always add a -H flag to see what the command does. So maybe you could show us with the BART crop tool, for example. So for instance, Volker uses BART crop with some commands, and if instead he types BART crop -H, then it will tell us how the crop tool is used. So when you're reading through these cells and some of the tools we just don't have time to go over in detail, then hopefully this will send you in the right direction.
Yeah, that's a very good hint.
I had a question. It's probably a naive question. Is there a reason why you picked 100 iterations? Like, sort of, what is the minimum or maximum limit of iterations that you want to sort of choose for this kind of reconstructions?
Well, in principle, better is more, but it's always a compromise, right? How much time do you have to run it? So these are like both the regularization strength and also the number of iterations is something that gets tuned a bit, right? So you would start with a lot of iterations and then figure out the right regularization strength, and then at some point you would decide, okay, actually something like 100 is okay.
Right.
Yeah, that's a good point. That also, when moving to these subspace recons, compared to a single static image, you generally do need more iterations for convergence because your problem size is getting bigger. So that's just another thing that you generally will see with dynamic imaging.
Thank you.
All right. I want to see if I can quickly add a poll question.
Probably another question would be, does this only work with the SSFP sequences, or you can use GRE as well and probably get something similar?
You mean like this particular type of reconstruction?
Yeah.
Well, I'm not sure how that would translate, right? So the idea is here, okay, you have a smooth signal, and when there is off resonance present, it would just shift your entire signal. So that is very particular with respect to this type of sequence, right? In a gradient echo sequence, of course, you also might have a like steep decay or so, but off resonance show up differently in your signal. So you don't get this kind of closed loop, right?
Yeah.
So the Fourier subspace would probably not be appropriate for anything that is related to like standard gradient echo sequences, I guess.
But that's a great question, because in the recipe, that's one of the first things you can check. You could see if a Fourier basis is good by projecting it onto a Fourier basis and seeing that your signal energy, just like the figure that Volker has here, if it's really captured. And there may be some other basis that's a better fit for your data.